Welcome to the session on Introduction to Graph Neural Networks using TensorFlow GNN API. Before we look into TensorFlow GNN API, let's understand what graph neural networks are and basics about graphs and where they are, some of the applications of graph neural networks and different types of graph neural networks as well. To start with, what are graph neural networks? So graph neural networks are specialized type of deep learning methods to perform inference on graph-based data. So there are different types of operations which can be done using graph neural networks, like you can perform node level predictions, edge level predictions, and graph level predictions on the whole as well. So graphs are all around us. If you see social media networks modeling or criminal associations modeling or building a recommendation engines. So graphs have got plenty of applications and even in drug modeling. And let's look at some of the important components of graph neural networks. It is the graph. Graph forms the basic component of graph neural networks. And the graph contains two components, which is the vertex, and vertex is the node, and edges, which is connects the one vertex to another vertex. So graphs are of two types. One is the directed graph and another is the undirected graph. So a directed graph will have arrows on its edges, and undirected graph will not have any arrows, which does not have any directions. So some of the common differences between traditional neural networks and graph neural networks. So graph neural networks operate on graph data structure, whereas traditional neural networks operate on neurons, and which are linear functions. And graph neural networks are much more complex than the traditional neural networks, because even for a single data point, you have to deal with multiple graph nodes and edges. And traditional neural networks are comparatively very easier to use, and when you compare it with the graph neural networks. Now let's look at the snapshot of history of GNNs, how GNNs evolved over the period. GNNs are not something which is new. It's been there from 2005, but it's just that in the last 5 years, it gathered a lot of momentum. So if you take graph convolutional neural networks, spatial methods were introduced back in 2005. And then we had some recent innovation in the form of GNN in 2016. But spectral methods were more recent. Around 2015, we had spectral graph convolutional neural networks and ChepNet. And then we also had 2017 some breakthrough in the form of MONET and Neural MP. And it's the last 5 years, there are different types of attention-based graph neural networks which had come, Graph+AI, and the other types of networks like relation nets. So this is the timeline of GNN history from 2005 and covering the different types of architecture which has come out in the last 5 years. When you take the applications of graph neural networks, they used in node level tasks, edge level tasks. For node level tasks, mostly it's a semi-supervised problem where most of the nodes are labeled. And for the nodes which are not unlabeled, you have to classify into one of the label categories. So in addition to node classification, you can also do, predict the partitions and affinities in the graph. When you take the edge level task, you will have to identify connections between the edges, and you should also, it's also used to identify state of objects and scene. So most of the edge level tasks are used to model social network interactions in a social media network, or to model criminal associations, or to model recommendations engines. These are all applications of edge level tasks. So in addition to these kinds of tasks, graph neural networks are used in a variety of applications like traffic predictions, modeling disease spread, etc. Graph convolutional neural networks are similar to CNNs, except for the graph that GCNs deal with graph structure data, while CNNs deals with Euclidean data like images and text. In addition to that, GNNs also operate on varying number of unordered nodes. GCNs are further classified into spatial graph convolutional neural networks and spectral graph convolutional neural networks. Spatial graph convolutional neural networks overcome some of the shortcomings of traditional GCNs. So the traditional GCNs lacks the ability to understand the ordering of neighborhood nodes in spite of having a geometric representation of graph vertices. So the way spatial graph convolutional neural network, overcomes this is by using spatial features to learn efficiently from the graph. And these spatial features are naturally located in this space. And to sum it all, you can say spatial graph convolutional neural networks is the proper generalization of GCNs and CNNs. The next type is about the spectral graph convolutional neural networks, which were introduced as early as 2005. And of late, there are some breakthroughs in this field as well. So spectral graph convolutional neural networks, defines the graph convolution from a spectral domain. And it mostly navigates around the research of graph signal processing, and this graph signal processing techniques like graph wavelets and graph filtering. And the spectral graph convolutional neural networks, it is mostly based on the spectral domain, and which itself is based on the graph Fourier transform. So graph Fourier transform might be a bit new, but it is just an analogy to 1D signal Fourier transform. And the next kind of approach is the GNNs with edge embedding. So most of the traditional GNNs, if you take, they just focus on the node level features. So GNNs with edge embeddings, in addition to focusing on node level features, also focuses on edge level features. Here, the edge level attention layers, they try to learn the node-based feature neighbors and the edge-based neighbors for each edge. And the next approach is the GNNs with attention, also known as graph attention networks. So graph attention networks overcomes most of the shortcomings of previously discussed architectures, and it leverages this concept of mass self-attention layers. So the way it works is it has multiple self-attention layers stacked on top of each other. And in each layer, the nodes are able to attend over the neighborhood features by implicitly specifying different weights for different nodes in the neighborhood. So graph neural networks with attention is definitely a better performing architecture in comparison with all of the previously discussed, GNNs. TensorFlow Graph Neural Networks is a high-level Keras API, which is used to deal with graph structure data using TensorFlow. TF-GNN is already internally used by Google to solve a variety of problems like dealing with, anomaly and spam detection, and also dealing with, traffic estimation, etc. It comes with an extensive tooling for working with graphs. So it has some of the features like tensor-based graph data structure, a data handling pipeline, and a plenty of models for users to get create prototypes very quickly. And this is an architectural diagram for TF-GNN components. We have a graph sampler, which is coming up soon, which is a data handling pipeline. Then there's a data structure for graphs, which is graph tensor. So this data structure is used by both APIs, DeepMind GraphNets, and it's also used by TF-GNN API. And there are plenty of examples for both of these model APIs for users to quickly create GNN prototypes. So TF-GNN API can be used in conjunctions with other types of models like ranking, deep retrieval, and for different kinds of neural networks for images and text as well. So this graph tensor is a data structure which can hold graph data, and it can be batched, and different kinds of data manipulations can be applied on it. And there are a list of library of operations which can be applied on graph tensor at the moment. There you can apply a plenty of broadcasting and pooling operations on nodes and edges, and a library of standard baked convolutions. And it's also an high-level API to quickly build GNN models. Now, let's quickly look at a code snippet to understand how the API is designed. So we have a GNN builder class, and this particular method contains the edge and node configurations, and we have assigned a weighted sum convolutions for the edges, and for each of the nodes passes through a set of DINGs interconnected layers after each update. And in the previous snippet, we looked at a very simple edge and node configuration class, which just uses the default setting. It is also possible to customize such classes. So here we have a weighted sum convolution class, which is more of a custom model architecture. So here we define the weights, weighted edges, and the pool edge values. And this pool edge values is the sum of all weights across the edges. So here, this type of custom model architecture helps us to assign, more weights for certain movies and genres in comparison with the others. So, which is more, applicable if you're building up a recommendation engines or graph-based recommendation engines, etc. So there are a lot of such customizations which is possible on the TensorFlow GNN API. We've come to the end of this session, and if you're interested in contributing to TensorFlow GNN API, you can check out the TFGNN GitHub repository. Thank you.